welcome everyone to this online event organized by OpenStack Europe community. My name is Zoltán Gombár. I'm head of operations of Open Telekom Cloud. This is also an OpenStack-based public cloud solution. I'm going to be the host of today's meetup, and let me just share you some information first about the agenda. We are going to talk about three topics today. First one is going to be about Containerlab by Vincentz Petzholtz from Arista Networks. Then there will be a session on NixOS by Arik Grahl from SysEleven. And finally, we will have a two-part session about a private chatbot solution and chatbots in general by Ferenc Kukucska and Nagy from Deutsche Telekom IT Solutions. The QA sessions will be moderated by Nils Magnus. He is also one of the organizers of this community, and I will just give the word right to him to talk a little bit about the community itself. Nils, the floor is yours.
Thanks, Zoltán. Hi, everyone. I'm Nils Magnus. I'm Community Outreach Manager at the Open Telekom Cloud, and I'm taking care of our communities and our involvement in communities in Europe and bringing users together here with cloud service providers. Have a strong relationship also to the Open Infra Foundation. And we set up this OpenStack Europe community, which has, by the way, now over 280 members, with the purpose of organizing events like this here on Meetup. This one is a virtual one. We had several instances of face-to-face events in different European countries earlier this summer, and maybe the next event that we are organizing will also be again a live event, maybe in Munich, but that's not completely confirmed yet, and we will let you know once we have those dates set. So we welcome all kinds of developers, engineers, architects who are passionate about exchanging their knowledge and information about their clouds, and especially on clouds that are beyond the hyperscalers. So that is our common goal here and the common topic. And well, I'm very happy that we have such a cool program today. So for both with some colleagues here from Deutsche Telekom and Open Telekom Cloud. But this is not just a telecom session, and that's why I'm especially grateful and thankful that we have two external colleagues here as well. So thanks a lot, Arik, and thanks a lot, Vincent, for your participation as well. With that said, I would like to hand back to you, and so we can get this started.
Yeah, thank you, Nils, for the introduction. As you might have already noticed, two of our speakers today are from Deutsche Telekom IT Solutions, or DTITS for short. And as our main partner, I would like to take a moment to introduce the company. As the largest ICT employer in Hungary, they play an essential role in driving innovation and providing top quality solutions to their international corporate customers in software development and system integration and operation. Since DTITS Hungary is a workplace that also actively supports professional development and knowledge sharing, it has been a significant contributor to our community, consistently offering resources and speakers for our events, just like today. And we are very grateful for their support that helps make these events to be possible. Please find their career page on this slide if you are interested in career possibilities within DTITS. Yeah. So with that said, there are some technical information to share. Firstly, today's session is being recorded, as I mentioned, so please keep that in mind also during the QA sessions. This also means that within a few weeks, the recording will be available on our YouTube channel. It is called Clouders Club, where you can rewatch the whole event and also previous recordings about meetup events. And so please, you can scan the QR code on the slide or find the link in the chat and subscribe for more cloud content there. So that's it. Thank you for your attention. And with that, I'm giving the word to our first speaker, Vincentz Petzholtz. Vincentz, the floor is yours.
Thank you very much. Today, I'm going to talk about like what you can actually do with containers in the networking world. Like what are the applications and implications of having this technology like containers? Because like the networking world tend to fall a little bit behind like VM and Kubernetes and things like that. But finally, we also have adapted and can make use of it. Just shortly, this is the agenda. So I'll introduce myself as well as the company I've worked for, but that's all the marketing you can get today from me because the topic in itself has any like relationships to any specific vendor whatsoever. In contrast, it's even vendor agnostic. So I will just briefly talk about that. And then what's even the challenge? So why are we doing this or why you should do it? And even also show like you can set it all up, which is, I would say, a more technical presentation. And if we have enough time at the end, so I kind of tend to overextend a little bit, then I can also spin up one topology just in the live demo, if the live demo gods are with us, right? Because sometimes they don't. And so then nothing works and you have no idea why, but let's keep it at that. So about myself, so I'm more or less a network engineer for the last 20 years in different companies and functions. Overall, I come from the technical side of things. But also made project management, procurement, so like done most of it in the industry. But now I switched to Arista Network, which is a network vendor. So we actually build the boxes and the software around it. But I had the pleasure working with and having pain under those other vendors as well. So I think everyone can relate. And I'm also an active community member at the Berlin Internet Exchange and also the German Network Operator Group, which is taking care of basically of the internet, if you will, or of the backbone side of things. So on Arista, if you never heard about Arista, just Google us. So we are around for 20 years. We build switches and routers and all the software around it, especially when it comes to automation and cloud networking. So just Google us and you will see if you never have really stumbled across Arista, then it's about time. I think market cap now breached 100 billion, so we are not exactly small anymore. And yeah, just give it a shot if you ever reconsider vendor choice. So what actually the challenge? Why are we doing this, or what can you do with it? So the context is networking with containers. And there are many different reasons why spend time with it. For example, you change profession, you want to learn another vendor, you want to learn certain protocols, you want to learn configure, troubleshoot, and all of that. And it has always been a hassle to actually set up like full-fledged networks in their original topology, like the production networks, right? And this has changed in the last couple of years, and there are actually like plenty of options you can pick from. And at this point in stage, I would say like most of them are a little bit obsolete because there are one or two which really stand out. So the options, I've tried most of them over the years, and in some cases it was just no fun. So you had like the time it took to actually set up your topology was extremely long. And you want to get testing and want to get learning as fast as possible. But those are the options you really run into when you want to simulate and build networks and then tinker with them. And Containerlab, obviously, as the name implies, is working with containers. It also supports VM-based appliances, but more about that later. So why Containerlabs? So it's pretty lightweight and easy to set up. So you usually have just a few components like Docker and Containerlabs itself, a couple of dependencies, and that's it. So installation is pretty straightforward. Documentation is pretty good. Obviously, it handles containers, so that means that when you want to simulate bigger topologies, you can make it quite efficient, right? So one node with a virtual or container Arista EOS takes about 1.5 gigabytes, for example, and then you can scale the topology as big as your bare metal or VM is. You can automate the whole process, so that means you can actually create and then destroy labs basically every 5 minutes. So it depends on how big your device and how fast your CPUs are. So you can really quickly create those topologies and then destroy them or recreate them if you later want to revisit something. And also a personal highlight is that since tinkering with Containerlabs quite a bit, I like run into bugs occasionally, and it's super easy to get in touch with the maintainers and the main author, and having like custom fixes shipped to me even in the past. So another reason is that it's completely vendor agnostic. So you can, there's supported guides for Nokia, Arista, Cisco, Sonic, Juniper, CRPD, Cumulus, etc., etc. And since some virtual network appliances are limited to like VMs and not containers, you can also attach VM-based appliances or images to your topology. Although I would recommend strongly to always try to keep things within containers because it's much more efficient. The overall vision of it all is that you can basically have a lab as a code or infrastructure as a code experience when creating those labs, right? So how do you get started? What do you actually need? So my personal setup is just a big VM, but you can also take a bare metal device. Usually it mostly scales over RAM. So if you want to have like big topologies with lots of nodes, you need a lot of RAM, and how much RAM each image or each container is consuming also, of course, depends on like what is the vendor of the image, how is the OS running, how efficient it is, right? It could be more with other vendors. So, but it's pretty straightforward, and we will just go through it. You install Docker, but Containerlab will even take care of that for you as well. You have to import images, and that's the biggest obstacle. We'll talk about that in a minute. And then you define the topology you want to run. Basically, you have one YAML file where you can just write it all down. There's a very good documentation on how to write it, and I can also show it to you, and then you can just start it up. And what Containerlabs will do, that it will take care of creating all the containers. It will link them in the way you described it, so you can create any topology you want to have. And you do not have to mess with Docker exec commands to do something within the maintainers because you have full SSH access to each node, just like in a real network. So you can then also push on the automation by using Ansible or other kind of automation tools with it. So how does it work? That's basically ripped off from the installation manual from Containerlabs. You can basically install it all with a script. There's apt-get support. You can also just install certain components. And yeah, there are even many alternatives to install it also. Just give that a look if you actually want to use it. And it's pretty straightforward. I've never seen this failed before, at least based on Ubuntu, right? And that's now we come to the biggest obstacle. And I got explained by our legal department that this has something to do with, legal reasons. And that is getting the images. So let's just say you want to have Nokia or Arista or Cisco. Then in order to create nodes, you have to have the images for the operating system of those vendors. Of course, you can also go with other open source stuff for sure, and you don't need any licensing or whatsoever for that. But you need to get those images, and usually when you have some contact to the vendor, it usually helps. In many cases, you can register yourself and can get software access and can download the container versions of the operating systems quite easily. But that's still an obstacle because many vendors do not throw the images out there without any authorization, right? Usually you have to at least create an account to get access to it. And by creating an account, you accept the terms and agreements. And that's sometimes important for the legal department, right? So that you basically agree to not do certain things with it, for example. When you have done that, and that's literally the command you are going to use for that, you download the image and then you can import it into Docker. And Docker is usually the container engine below Containerlabs. But I guess you can also use Podman by now. And then you have those images available to you. And the names you're using here are important. Then you have, before you actually start, you have to think about like which kind of topologies you want to build, right? And I don't know how many network engineers or networking people are here, but usually you have like a very data center centric topologies like spine leaf or core access distribution, or you have like more service provider use cases like you build rings and like double star topologies, or you mix all of those. And with Containerlabs, you are completely free to go to build any topology you like, but you need to, define it before you can even actually get started. So that is just an example of how a data center fabric could look like. So we have two spines on the top with some links, and Containerlabs allows you to completely describe everything in this topology just with one simple text file, and we will take a look at it at the moment. But yeah, this is just an example. It could look completely other way. And if we got time for the demo, then I can also show you how to build it. So it's very straightforward. You create a YAML file, and then you will have, you define the nodes. You can also define group criteria that you can inherit. For example, the image version I then inherit based on the kind. And there's also a group which has something to do with visualization, because when you build those topologies, you can also tell Containerlabs to visualize how the topology actually look like as a graph, like as a topology graph. And the next part, you defining all the links between the nodes. And so that's really, really straightforward. And you do not define really the endpoints because that are the nodes. And the links are like point A, point B. And then you say, well, this switch or this device on this interface is going to be connected to this other device on this other interface. And that's like as simple as it gets, right? With other, I'd say, tools, you have to make those mappings manually, or you create a segment and then you attach VMs to it. And then there's plenty of like room of error you can do with that. But here you have everything in one spot, more or less. That's how it looked like, but hopefully I can show you also on the demo. You have the command is actually just Containerlab deploy, and then you hand over the topology file, and then it will like take off and build everything for you and let you know when it's done. And what's also very nice about it, that it will create SSH aliases for all the containers by name. So you do not even have to remember any IP addresses. You just SSH, you just SSH into the containers. Deutsche Bahn is always trying to get in the way. I don't know if you have seen the notification on the top. Okay, so by the end of the deployment, you will get an overview where you get the name of the lab you define, and then the name of the actual nodes is appended. You get all the images, versions you have deployed. You can even mix and match different vendors and versions within the same topology. So I was just lazy in this topology. So that's why I've created only Arista containers. And then you will get the IP addresses of the management interface, because then you have an out-of-band management on those nodes. And then you create an in-band as you wish. Yeah, then you can, this is just a demonstration in case the demo doesn't work. So you SSH into the node. You can see there the CLab sysadmin friends DC1 leaf 1. and I can just SSH to the name directly because Containerlabs have add those into the etc host or SSH config for me. And then I can already start working, do a show run, and I can see like this is regular configuration, and I can start configuring. Yeah, and this is just an example of a configuration you could do. And of course, this is not only simulating in a way that you not really creating the network, but you can actually also send traffic through it. So even below like the network engineers, so the engineers working for vendors, they also quite use this heavily because we don't have hardware lying around, as everyone would guess, for all the use cases, right? Of course, there's hardware we can use, but usually it's just faster to build it virtually. And in most cases, if the customer has bugs or something wrong going on in the configuration, then you can reconstruct it completely virtually. And I would say 95, 98% of the problems can be solved without any hardware. Yeah, so in summary, you have a single line deployment. You just make Containerlab deploy. It auto-populates everything for you. It takes care of the management. You can even hand over the configuration of the nodes. So you can either decide to automate the configuration after the containers have spin up, or you can even hand over text-based configuration, which is then mapped into the operating system of choice. And then the node will come up with a complete configuration if you wrote that before, or you can do it afterwards, right? And it will set up all the links for you. But decommissioning is as important as deployment, because after some time you will just, will get stomped, and the utilization of your devices will be just too high if you let all of your Containerlabs running all the time. So it's very important to think of like build fast and then destroy fast when you're finished, right? And you can just save everything into a Git repository or whatever you want to do with it, and then you can even reconstruct it later on. So you would rather, make and destroy on demand. That's just another use case, what you could do with it. So once a year, there's a conference called DNOG, where network operators organize. And for a workshop of DNOG, I've run a topology which assembles a classroom. So where everyone in the classroom has one container, and then all the containers are interconnected with each other in a certain topology. And then every one of the attendees in the workshop room had to talk with neighbors in order to establish BGP peering or just IP connectivity or whatever it is. So you can build just amazing things with it. So there's a classroom video, hopefully it works. So that is actually the graph that Containerlabs will generate for you of that classroom. So we had like 50 people in that, and you can visualize that after Containerlabs have spun up. And you can see the vast amounts of links. I don't know, it was like 500 or 600 links in total. Of course, you auto-generate those links with a script, and then you can recreate the whole classroom setup in just a couple of minutes. And always remember, get rid of your old labs, right? So, and you can also say, I want to, shut down the lab, but I want to maintain the configuration which I might have done in the lab by hand. And Containerlabs will make sure to save all the file system of all containers in a subdirectory where you have your topology file. So when you spin it up and you do configurations and save it on the nodes, this will be saved outside of the containers as well. So when you spin it up the next time, it can take the configuration, or you can just back up it or whatever you do. Okay, I have no idea where I am in terms of time. I think I was faster this time. I think I still have 10 minutes, something like that. So this QR code will lead you directly to my LinkedIn page. So just in case you're interested in Containerlabs or in Arista, then just shoot me a follow or a connect on LinkedIn. And this is already the end. And I think we got some time for the demo. And so I will just spin up a small container for us. Okay, let's see. Okay, so I will show it to you I've pre-created in this case to save a little bit of time, but it's really just a text file. So you have to define a name for the lab, which will also make sure that when you create multiple labs and you use the same names as the nodes, then the name of the lab will also will be prefixed before the names of the containers, so you can use the same container names all the time, but it will not clash because of the same names, because of this lab prefix. I defined the image not per container, but just per kind. So making inherit that. I've created 2 spines, so that's the topology I've shown before. So that's basically this topology. No, this one. So this is actually this topology, and that's all the nodes, and this is these are the links. So that's really all there is to it, and now I usually have a small start script, but I will do this by hand now. And now we will spin up the topology. So it's very easy. Or just Containerlab deploy, and then I hand over the topology file, and then it will spin up the lab for me. So the more CPU power you actually have, the faster you can deploy more containers at the same time, right? So, but if you want to scale bigger, then RAM is basically the key metric. But if you want to scale even further, you can also do that. There is a project called Kubernetes from the maker of Containerlabs, which takes Containerlabs into a Kubernetes cluster, where you can then distribute your complete topology across different VMs or nodes, and then make your topologies huge. The classroom topology I've shown you with approximately 60 nodes, so 60, was running on a VM with 64 cores and then 128 gigabyte of RAM. Okay, so that's already running. So I can then now SSH into the container and can do whatever. Maybe I will try to show the graph as well. If it sometimes doesn't work because another graph is already running because I'm stupid. Oh no, this time it works. Let's see. So you can just hand over the lab. Oh, here we go. So I've just taken the link. This is actually the lab we've just created. It's a little bit chaotic. You can also make group variables to it. So on the topology file, in order to make it look a little nicer, right? So here we have the spines, for example. Here's the leaf, here's spine 2. And you can group that so you have different, actually different levels, let's put it that way. And that is leaf 2, right? And that is roughly the topology from here.
Impressive.
Okay. You just have to try it and have fun with it. I really encourage you to try it out. It's completely open source, and I can tell you that not only one vendor is using it like Arista, but also other vendors are using this internally for a lot of stuff. And I try to show it my customers as well, so they can, simulate everything on their own and not depending on everyone else. Okay, I think I can give some time to the next speaker then, because I run out of content. So
yeah, well, thanks, Vincent. We have actually a few questions from the audience, and I would like to remind you that if you are interested in asking a question directly, then just raise your hand. There is a small hand icon on the, at least on my screen, on the lower side of the screen, and with that we can turn on your microphone as well, so if you want to ask something directly. But what was there in my stream? Yeah, okay, here. So someone asked, so can I run all kinds of networks on all OSI layers, not only TCP/IP, but also on, say, strange layer 2 protocols, or do some asymmetric routing or something like that? Is that also possible?
Yes, so it's quite frankly a complete a physical link completely done in a virtual way. That means that you can run ISRS, LDP, CDP link layer, other link layer discovery protocols. You can also do LACP. So you can really also incorporate all the most of the physical aspects of network, which are not, of course, not existing on the containers for real, right? So yes, you can simulate all kinds of topologies with all kinds of protocols. It's not bound to TCP. It's not even bound to IP. So you can do all kinds of also layer 2 transport, MPLS. You can do the whole forwarding plane is quite intact, but that is, and that as a disclaimer, that depends on the vendor image you are using, right? So when you, it appears different when you take an Arista container EOS or a Cisco or a Nokia one, then you have to respect the feature set with the containers are coming with. But Containerlabs in itself does not limit that too much. So it needs to be supported by the container image more or less. Then there I see the question: are there any bandwidth issues if simulating real big topologies? So I haven't seen any. So you can send traffic through it. There's even a virtual Ixia appliance. So if you know Ixia, which is a quite sophisticated vendor for traffic generators, there's a virtual and free to use Ixia appliance for supported in Containerlabs. It's a little bit complicated to set it up because it has multiple components, and you have to steer it with, you have to configure it with API calls. But if you ignore that, yes, you can send traffic through it. With container EOS based on Arista, for example, the links are physically 1 gig, right? So all the links are more or less 1 gig, and that's it. I'm not even sure if other container images are supporting higher speeds. But that's what you're going to get when, for example, you work with Arista container images. But I have never had issues not have been able to send enough traffic through the topology, right? Because you can do iPerf, you can do ping, you can do whatever you like, and you can also just attach Linux containers with whatever tools you want to have into it as well. And then, yeah. And then you tell me if you tested it more. Then what I also can see as a question is, what should I do if my hardware is not yet available in the repo? Where I can contribute? So you can find that on, so the maintainer is a really, really nice guy. His name is Roman from Nokia Networks. And I think he's quite open to pull requests when you use GitHub, right? So Containerlabs is on GitHub. You can just search for the link. I have the link. I have the link in the presentation, right? But basically, you can contribute here, and also the Containerlab documentation is amazing, right? So
how hard is it to actually add some support of a new platform?
It depends. Is it like a commercial vendor image you want to try out? Then you need to engage with the vendor if there is a native like container version of it. Then if you're just an end user and you do not have the rights to do it, then you can, you could still try to contribute it, right? If you make it work. But you have to just try it out. I mean, those containers are normal Docker containers. The images are normal, like it's not even close behind Containerlabs. So, and there are a lot of guides on the other vendors as well. I think you could, there's enough information to make other vendors work, even if they are not container but VM based, but it depends, right? And then if you know how to get it work, then you could contribute to the Containerlabs documentation.
Okay. Yeah, there's an impressive list of vendors already in there. When I last checked the repository, that's cool stuff. Yeah, especially for the networking colleagues. Really cool that you so easily can simulate also more complex setups, because if you actually have to carry around all those boxes for that and doing the actual cabling and so on, it's
so as like, especially for OpenStack, when you use like pure IP layer 3 fabrics or VXLAN EVPN fabrics, you can basically simulate the whole fabric and then troubleshoot, reconstruct bugs, test configuration. You can even build digital twins of your production network, like very close to production with Containerlabs, and then spin it up also with pipeline, if you like, and then make your tests and then tear it down again, right? So the possibilities are really like really good. But yeah, I think I run out of time finally.
Okay. Thanks a lot.
Next one.
For your presentation. Then I think we can already switch over for the next session. The next session will be run by Arik. I don't know, are you?
Yeah, hello. Okay, hello everyone. Welcome to my talk. Today I want to give you a brief introduction on NixOS and its basic principles. This presentation can be found online by just scanning this QR code here or entering this URL. Before we start, let me introduce myself. My name is Arik Grahl and I work at SysEleven. SysEleven is a Berlin-based hosting company. We have data centers in Germany and a dedicated network infrastructure. We have an OpenStack-based cloud offering and a managed Kubernetes sitting on top of it. My team develops the highest abstraction layer, which is a software supply chain management system and an application lifecycle management on top of this stack. My daily business mostly deals with Kubernetes controllers and operators, which we develop in Golang, and of course, packaging with Nix. If you like to reach out, you can contact me via any of these channels. Nix is a hopefully overloaded term. Therefore, let's start by answering the question what Nix actually is. In this figure, you can see that Nix is often used interchangeably for the language itself, which I will call Nix DSL to make it more clear. On the other hand, the term Nix is often refers to Nix package, a large package ecosystem on which NixOS is built. Even for this operating system, NixOS itself, the term Nix is occasionally used, which is confusing in particular for newcomers. We will now turn our attention to these three pillars of the Nix trinity. The Nix language is a purely functional language. This means that any valid piece of code is an expression returning a value. When evaluating a Nix expression, this returned value will always yield a data structure. In contrast to imperative programming languages, there's no sequence operations to be executed. Let's have a look at some examples to get a rough idea about this language. By the way, you can almost all of the examples are testable in this presentation if you paste them in a Nix REPL. When we are evaluating the string foo, the same value of it will be returned. It is the same for more complex data structures. When we are evaluating the attribute set x equals foo, it will return the value of the same data structure. We can define a variable f with a static value of the string foo. If we are evaluating this variable, it will return the string foo. Now let's store an anonymous function under this variable f. It receives the argument x and returns the very same argument. When we're calling the function behind the variable f with the string foo as an argument, we will receive its value back. You might have already noticed that there is no notion of strict types in this example. This is why Nix is dynamically typed. It means we might as well pass an attribute set x equals foo into the same function exposed via the variable f. Another interesting property of Nix is that every function is unary, which means it accepts exactly one argument. In order to construct functions which consume 2 or more arguments, we make use of a concept which is called currying. We use a so-called high-order function which receives another unary function as an argument. In our example here, we are implementing a concatenation with a space in the middle of the arguments a and b. For the caller, the function behind the variable f looks like a single function with 2 arguments, where the strings foo and bar are passed. While this is common in Nix, an even more idiomatic way of passing series of arguments is by encapsulating those in an attribute set. One last time we are using the variable f to store an anonymous function which receives an attribute set with the keys a and b. Otherwise, it is the same implementation of our concatenation with space from before. We can now call this function with a respective attribute set as argument, where we are assigning the strings foo and bar to the keys a and b respectively. So, okay, I promise, this was already the most complicated slide regarding functional programming, and it won't get any worse. The second property of the Nix language is that it is lazy evaluated, meaning that only this part of the expressions are actually evaluated where its results are requested. This is crucial for large code bases like Nix packages, where you usually only want to build a certain package and not the entirety of packages known to humanity. However, the disadvantage lies in the fact that some errors only surface when the respective execution paths are taken. This example illustrates lazy evaluation. We have an attribute set with the name a, which stores under the key x the static string foo and throws an exception for the evaluation of the key y. When evaluating the key x in this attribute set, we will successfully receive the string foo. On the other hand, when accessing the key y of the very same attribute set here, it will crash with the respective exception. The language Nix is purpose-built. It means that it is a domain-specific language serving the Nix packager. It can be used beyond that, and it was used beyond that, but it was never designed to be a general-purpose language. Don't be frightened. I will now show you a real-world application of the Nix DSL. You're not to understand it in depth, it's just to get the feeling how the language is actually used. This is the package of setup env-test, which is a common project used for testing Kubernetes interactions. Now, since we have an understanding of the underlying language, we can take a look at the primary purpose of its serving, which is the Nix package manager. Nix packages is often used synonymously with the package manager, which is primarily a large monorepository on GitHub. In fact, it's one of the largest repositories in terms of size, contributions, and contributors. The monorepository approach makes it easy to define a complete build chain for building all different kinds of packages. This is a basic user space like busybox or core utils, a compiler, and also dependencies in form of shared libraries, up to sophisticated kernel modules. Since all components are included and therefore versioned in a self-contained way, it allows reproducible builds, even for arbitrary historic snapshots. Nix packages is large, very large actually. With more than 100,000 packages, it easily outsizes other established repositories. You will find among classic system packages also a variety of language-specific packages, such as for your JavaScript, Python, or Ruby. Here you can see the top 10 sets included in Nix packages, reaching from scientific purposes like R, Haskell, Python, or Camel to editor-specific packages like Emacs or Vim. At least in terms of amount of packages, Emacs seems to be dominate over Vim here. Given the gigantic size of the repository, one might assume that the majority of the packages is rotting away. Surprisingly, this is not the case, and most of the packages are pretty up to date. For well-known repositories, this visualization here shows the number of packages compared to the number of fresh packages. In the top right corner, you'll find Nix packages unstable, and next to it its versioned variant Nix package 24.5, which is slightly less up to date. The Arch user repository is the closest in terms of amount and packages, but has significantly fewer fresh packages than Nix packages. The cluster Debian Unstable and Ubuntu 24.10 is fairly fresh, but has roughly only a third of the packages. Another cluster with even lower amount of packages, but reasonable freshness would be Fedora 40 and Gen 2. With a powerful package manager and ecosystem in place, we can now finally have a look at the operating system, which builds on top of all this, NixOS. It is a Linux-based operating system with an immutable design and an atomic update module. With such ambitious and modern design principles, I find it quite remarkable that it was released already 20 years ago. It supports major CPU architectures, such as the 64-bit versions of x86 and ARM. There is experimental support for other architectures, but since it lacks a binary cache for build artifacts, it's not too much fun to use. It is licensed very permissively under MIT, which permits usage within proprietary software. NixOS has many benefits, but in my opinion, the unique selling proposition revolves around the single configuration file that describes the entire system. When I say single configuration file, I already lied to you, because usually a NixOS system is composed of two configuration files. For practical reasons, one is a hardware-specific file, which is mostly commonly generated during installation and will typically not be modified, unless you change the hardware of the system. The second configuration file is a hardware-agnostic one and mostly deals with generic service definitions. Let's get quickly over a more or less minimal example of such a configuration file to get a rough idea how such a file can look like. Through the Nix module system, the hardware configuration file I outlined earlier is imported. We defined an EFI system with a systemd bootloader. As we will see later, treating this bootloader as a first-class citizen in the operating system brings a lot of benefits to the table. We are using the latest standard kernel, which comes with NixOS. Batteries are here also included. It will come with the needed kernel modules defined by high-level service definitions, such as a hypervisor or anything like this. Setting up the time zone system-wide is done as everything in NixOS in a fully declarative fashion, and other localization options would look similar to this. Usually, a NixOS end-user software is not installed directly as you would normally do in other Linux operating systems. Instead, you define the desired set of end-user software packages to be installed fully declarative. In this example, only the editor Vim is installed. The installation of software in NixOS usually follows a completely declarative approach by defining high-level services. Instead of defining software packages to be installed, we define the capabilities or the service behind it. If we want to be able to run containers, for instance, on our system, we simply set virtualization podman.enable true. All necessary kernel modules will be then loaded, and also the necessary user programs will be provided automatically. Last but not least, we specify the state version, which reflects the entirety of the options available in our NixOS configuration here. This is mostly independent of the actual software versions. NixOS options are very powerful, and they provide the declaration of a cascade of complex services. Very useful is the property that the lifecycle of the defined services is managed automatically by Nix. It is almost never necessary to manually evoke systemctl restart or like after a new configuration is rolled out. This service section outlines a definition of a system which is exposed via SSH and runs a Kubernetes node. It is quite idiomatic to specify enabled equals true in order to activate the said service. Other configurations like the root user to be able to log in or the role of the K3S node can be also specified in the respective service definition. In NixOS, an update, an installation of a new package, or a reconfiguration of software all lead to a generation. Since everything is declarative, with NixOS Rebuild, one can reapply the current configuration. If there were no changes to it, the system will stay unaltered. To receive updates, one would either update the respective repository channel or use the -- upgrade flag to do it automatically. Another interesting attribute is to decouple building and rolling out changes. With the verb switch, you would directly roll the changes out once they are built, thus making them available directly. The verb boot, on the other hand, just builds the changes and marks it as a boot target for the next reboot. Remember the integration of the bootloader as a first-class citizen, which I mentioned earlier? NixOS exposes every generation as a selectable boot target. So every change can be easily and safely reverted, but by simply booting into the previous system state. Generation can also be explicitly rolled back with the corresponding flag in NixOS rebuild. Since those generation and lots of old versions tend to pile up over time, one can garbage collect the unreferenced artifacts or delete them even on a time-based policy. So let's have a more practical view at NixOS. In order to save precious time waiting for commands to finish, I will present my demo here in this presentation. The first use case we are looking at is to update our system. In particular, we want to perform a kernel update. Initially, we are on version 6.11.0. Since a kernel update can't be performed online with NixOS, we want to boot into the kernel after the next reboot. Therefore, we are using the verb boot when invoking NixOS rebuild. To check for new versions online and not simply rebuild the very same configuration we are having before, we are also using the flag -- upgrade. As specified, it is pulling the channels for update and building the new system configuration. With Nix rebuild list generations, we can see that there exists a new generation with a new kernel, which isn't active yet. When the reboot of our system is done, we will be prompted with a similar overview of generations in the bootloader. After the system is up and running again, we rerun NixOS rebuild list generations and can see that now the new generation is marked as current. Rechecking the current kernel verifies that this update was indeed successful. So we are now on 6.11.3. The second use case we are looking at is to install new software. On a higher level, now we want the system to become a Kubernetes node. First, we check if it already runs Kubernetes by executing kubectl get nodes. And we can see that not even kubectl is installed. Now, instead of installing all the Kubernetes-related packaging, configuring and bootstrapping the cluster, we go back to our initial requirement. The system should become a Kubernetes node. This is what we are adding to our Nix configuration. For sake of simplicity, I'm using the lightweight K3s distribution, but there's also a Kubernetes vanilla option available in Nix. Now it is time to roll out this configuration. Now we are more impatient and want to avoid another reboot and directly start the Kubernetes node. That's why we are using the verb switch now when running NixOS rebuild. Since we have just upgraded our system, there is also no need to specify the -- upgrade flag again. You might have noticed that in addition to the building of the system configuration NixOS setup, the etc directory is set up here, and the systemd unit k3s.service was started. Now we are running NixOS rebuild list generations again and see that we are directly in our follow-up generation. Since we haven't updated the NixOS version, it will stay the same in comparison to the previous version. To verify our configuration, we rerun the command kubectl get nodes and indeed get a successful response. NixOS hasn't just conveniently provided the kubectl CLI, but more importantly has configured and started a Kubernetes cluster. A production-ready multi-cluster setup wouldn't be any significantly more complex. You might ask yourself, how can Nix possibly deal with such complexity? The answer lies in the fundamental theorem of software engineering, which states all problems in computer science can be solved by another level of indirection. This theory is postulated by the British computer scientist David John Wheeler. Let's illustrate this theorem with a simple example. The binary of the well-known application rsync. We can see that Nix exposes this in a quite unusual path. More interestingly, if we follow this symlink, we see that it's actually pointing somewhere else in the Nix store. This is the central structure where all artifacts known to Nix are stored. All artifacts? What about configuration like this weird path? As we can see, this directory is a symlink to a Nix store artifact of a system path. And what is now this run current system then? Again, it's a symlink to a Nix store directory representing the generations we have just seen earlier. So to sum it up, our simple rsync binary is actually a cascade not of 1, 2, but of 3 symlinks. The next question is, why stop with the indirection at the binary? Can't we go deeper? Sure, we can. What about the dynamically linked shared libraries like glibc and the like? If we list those for our binary, we will see that this is dynamically linked and shared libraries are against the references of the artifacts in the Nix store. This makes NixOS both very flexible in using all different kinds of library version combinations, as efficient in reusing those shared libraries among different binaries. This brings us to the second, less famous part of the theorem. All problems in computer science can be solved by another level of indirection, except for the problem of too many layers of indirection. In fact, Nix is doing a great job to handle this and fully abstract it away for the user. I want to continue my talk with another interesting use case of Nix beyond the previously highlighted ones, which is to use it as a container builder. You might wonder why not stick to the established traditional Docker build. Generally, for most users, there is nothing wrong about using Docker to build containers. However, you should be aware that it's not even close to being deterministic. Most people don't notice it, and the majority of the cases it doesn't matter. But in some situations, it might be crucial. Another downside is that often a package manager in some Linux distribution repository is used to compose packages inside the container. In my opinion, this is simply a waste of resources and unnecessarily increases the attack surface. You might want to address this problem by using multi-stage builds and avoid it, but then the layering and therefore caching of different dependencies is still pretty poor. The good thing is Nix can address all of these issues. Let's find out how. We are assuming that you are a Golang developer and have this simple web application. Again, you're not supposed to understand this in depth, but just let me briefly outline it. It listens on the TCP port 8080 and serves an HTTP server here. Every request it calls a downstream server via HTTPS to retrieve the weather data for Berlin. Nix brings convenient functionality to build software for all kinds of languages, which also applies for Golang. We specify simply a package name and a version. As the source input, we are using the current working directory where our Go code lies. Since we are good with Golang standard library and do not need dependencies, we can simply specify an empty vendor hash here. This is all we need to build the binary only with Nix in a fully declarative and reproducible way. Wrapping this now into a container can be achieved conveniently with the build layered image functionality. It accepts a name for our container and a tag where we are setting the version. You might have noticed that we are depending on a CA chain to initiate a TLS connection to the downstream weather service we are using. Therefore, we define the package CA-cert to be part of the container's content. By referencing the output of our previously defined Golang binary, as the entry point for the container, it gets copied into the container implicitly and in a fully declarative fashion. We then build the Nix expression with Nix build and getting a result symlink in our working directory, pointing to the final artifacts in the Nix store conveniently. This is the container image as a gzip tarball and can be loaded with the container runtime of your choice. We then can run this container while exposing the TCP port 8080. With an HTTP client, we can check this endpoint, and indeed, it is returning the weather report for Berlin. Let's sum up today's content. Nix is a powerful language which satisfies different use cases around packaging and configuration management. Nix Packages is a large and attractive ecosystem, both providing packages and convenience functionality to build such. NixOS is a production-ready and flexible immutable operating system with an atomic update module. Building containers with Nix offers both the desired properties of Nix while not breaking existing tools, thus making it, in my opinion, a perfect candidate to start with. If you'd like to read more about Nix, I recommend these resources. This brings me to the end of the talk. I hope you like it, and I'm happy to answer some questions.
So thank you so much, Arik. This was an amazing roller coaster ride, indeed. Let me see. We have a few questions there. So, for example, someone asked, where can I find the NixOS options to configure and packages to install? So, probably is where is the overview and
you can find it in my further reading slide. You can find it on search.nixos.org. It has a convenient functionality to search through all of those 100,000 packages and also get all of the options there conveniently. As well, the GitHub repository of Nix packages itself is a great resource.
Okay, cool. And let me just check for the other questions. Here we go. There was a question regarding cloud setups. Where is it again? Okay. How is NixOS beneficial in a cloud environment like OpenStack?
Most of it benefits for NixOS derive basically that it's an immutable system and that it provides automatic updates. So this makes it, in my eyes, a perfect candidate to use it in cloud environments. You can build NixOS offline in some sort of CI environment and have like fully flavored images ready to build. So you can even do partition schemes in it, rely on all the magic numbers, the partition UUIDs in it, and then simply have like images which are ready to be booted in the environments.
Do you run such setups yourself?
Yes, we do. Privately, I'm running all of my infrastructure on NixOS. I'm operating a multi-node Kubernetes cluster on it. And also we are adopting it here at SysEleven slowly but steady. It's not yet in some sort of production environment. We are rather using at the package use cases, which is where we use it for packaging of the Kubernetes workloads itself. So we are basically using it to package YAML files. However, you can also use it for classical system engineering approaches of packaging of binaries.
So Christian asks, would you trust Nix or NixOS for real production environments, or would you recommend this just for some development stuff?
I would trust it for a production environment. I would consider it production grade. Yeah. So I know also a few of companies larger than SysEleven who use it in production. So I think it's good to use it there.
And maybe a final question from Martin. What is the most significant benefit or which application for real-world applications?
Well, it depends. If I would have to pick one, I would say, again, this service functionality of Nix is the most powerful Nix option I know, because you can define a cascade of different network services in one section, and it will take care of all the intermediate steps which are necessary. For instance, if you define a set of network services, You will get also the correct firewall settings for it. It will fit together. You won't have any missing links in between those services. So I guess for medium-sized network applications, which you would traditionally run and set up on a VM, I think NixOS can be a very good alternative.
And where would you, this is the last question I have here on my list at the moment, where would you draw the dividing line between classical infrastructure as code environments or platforms like Terraform or Ansible and so, and NixOS? So, I mean,
NixOS can replace a majority of this infrastructure as code and configuration management components, I would say. So, for instance, our team doesn't use Ansible or Terraform anymore. We are using a very lightweight API where we define Kubernetes workloads, and the rest is literally just Nix. So it's quite powerful. This is a fleet of Kubernetes cluster we are managing with it. So it's totally viable actually to completely refrain from using these tools, since there are a lot of tools in the Nix space which can act as a replacement while adding functionality which is beyond the scope of a single node. So this NixOS configuration I just outlined has more the scope of a single node, while these tools basically compose this configuration into a broader context where you can then define a fleet of nodes with only by means of Nix. So if you're interested in this, I would look out for NixOps.
Okay, good. Is there something I missed? I think that's all at the moment. So with that said, thank you a lot, Arik. And
pleasure.
I think we can hand over to you, Zoltan, for the introduction for the next session.
Thank you, Arik, and thank you, Niels. Before continuing, let's have a short break of 5 minutes, and we will return in 5 minutes. Thank you. Let's continue with our next presentation, Ferenc Kukucska, regarding AI chatbots and OTC private chatbot demo. Feri, the floor is yours.
Thank you very much. So, hello everyone. Welcome to our demo practical LLM chatbot solution on OTC. My name is Ferenc Kukucska. I've been working in the Big Data and AI squad for 4.5 years now as an architect and have been in the AI industry since 2017. In these past several years, I worked on many interesting AI projects, recommendation systems, intelligent search engines, chatbots. But in the last couple of years, I'm focusing much more on DevOps projects built with technologies like Kubernetes, Argo CD, Helm, Terraform, and you will see each of these as a building block in our presentation today. My fellow presenter is Zsolt, who will cover the technical parts in the second segment.
Thank you very much, Feri. Hi, everyone. My name is Zsolt Nagy. I'm architect in the Big Data AI squad. My primary focus to doing DevOps tasks and also supporting data warehousing, big data, and recently to the AI services. I give the ball back to Feri.
Thank you, Zsolt. So first, let me present you the key milestones of chatbots. The history of chatbots is quite a fascinating journey. It spans several decades and involves significant advancements in artificial intelligence and natural language processing. I will show you a short overview of the key milestones in the development of chatbots. So the first one, Alan Turing, pioneering computer scientist. You can see the photo of the slide. On the slide here, he proposed the idea of a machine that could present intelligent behavior that one couldn't distinguish from human's behavior. So this concept became known as the Turing test, laying the groundwork for future AI developments. In 1966, Joseph Weizenbaum at MIT developed Eliza, one of the first chatbots. Eliza could simulate conversations by mimicking psychotherapists. It was able to hold simple conversations and demonstrated the potential of natural language processing. In 1972, Kenneth Colby, a psychiatrist, created Perry, a more advanced chatbot designed to simulate a person with paranoid schizophrenia. So Perry was considered an improvement over Eliza due to its ability to simulate more complex and human-like conversations. In 1970s, Rockter was a chatbot capable of writing prose and poetry, but much of its output was pre-written. Jabberwocky aimed to simulate a natural human chat in an entertaining way and learned from the past conversations. In 1990s, Richard Wallace developed Alice, which was the artificial linguistic internet computer entity. It used AI/ML, so artificial intelligence markup language, and created more sophisticated conversational patterns. The Loebner Prize in 1990, it was an annual Turing test competition, and it encouraged the advancements in chatbot technologies. In 2000, Smarter Child chatbot developed mostly for Windows Slice Messenger or MSM Messenger, provided users with information, entertainment, and conversation. And in the end of the decade, businesses began deploying chatbots for customer service, support, and marking the beginning of the commercial chatbot use. And in 2010, Apple introduced Siri, a voice-activated personal assistant integrated into iOS devices, and Amazon's Alexa, Google's Assistant followed, integrating the voice recognition and natural language understanding. And in 2020, OpenAI's ChatGPT 3 was introduced. It represented a significant leap in AI and NLP capabilities. It could generate human-like text based on deep learning and has been used to power various chatbots and virtual assistants. So throughout these past 70 years, chatbots have evolved from simple rule-based system to sophisticated AI-driven entities capable of understanding and generating human-like text. So before diving into the LLMs, let me cover what language models, so LLMs, are. These are a type of AI that are designed to understand, generate, and process human language. So they are trained on large data sets of text and learn patterns, relationships, structures in language to predict and generate text. Now let's define LLMs. So LLMs are learned utilizing self-supervised learning and semi-supervised learning on enormous amounts of unlabeled text, as opposed to the TLMs, traditional language models, which are trained on labeled data. So LLMs are mostly general purpose models that can be good for a variety of tasks, so they are not trained for a single job. These traditional language models are pre-trained by mostly academic institutions and major tech corporates, so LLMs are rather self-training. So they get better with the more output and usage they receive. Let me cover some LLMs applications. So natural language processing tasks, for example, text generation, text summarization, translation, conversational AI and chatbots, so virtual assistant, customer support. Also, they are very good at code generation and debugging, like suggesting code solutions, write code snippets, writing the documentation part of codes. Search engines and information retrieval can provide improved search results, and contextual question answering like ChatGPT. Besides these, LLMs are also very good nowadays in healthcare, education, entertainment, like video games, NPC interaction, script writing in the movie industry, and so on. About LLMs architecture. So the core of the architecture of LLMs is based on transformers, which enables them to process language efficiently and accurately by using self-attention, multi-headed attention, and feed-forward layers. So the key distinction in various LLMs lies in how they are utilizing the transformers encoder and decoder blocks, how they are trained, what specific tasks they are designed to. And finally, some popular LLMs, so BERT, bidirectional encoder representation from transformers, is developed by Google. It's a transformer-based model that has attained cutting-edge performance. performance on a variety of NLP tasks. GPT-3, Generative Pre-trained Transformer 3, is an OpenAI transformer-based model. It can produce languages, that is a human-like and with a high degree of accuracy and fluency. And transformer-based model called Roberta. Roberta is a robustly optimized BERT pre-training approach. It was created by Facebook and has attained state-of-the-art performance on variety of NLP tasks. Let's take a look at the comparison of private and public chatbots. So as for the accessibility of private chatbots, they are restricted to specific groups or organizations. Access is often controlled via user authentication mechanisms such as passwords, tokens, or enterprise login credentials. Use cases, as you can see, internal support, helping employees with IT issues, HR questions, onboarding processes, enterprise applications. So assisting with business processes like project management, data analytics, workflow automation, and education. So used within educational institutions to help students with information, scheduling, administrative tasks. So these examples, internal IT help desk bots, are used within companies to help employees with technical issues, HR chatbots helping employees navigate the benefits, payrolls, other HR-related questions within an organization, and educational bots, as I mentioned. These are good at deploying with schools, to have students with course information, administrative tasks. As for the data privacy, private chatbots deal with sensitive organizational data and typically operate within secure environments. So the key points here are the data governance and policies and industry-specific regulations that ensure the confidentiality and integrity. Now let's dive into the world of public chatbots. So the accessibility. The public chatbots are accessible to anyone, so they are often integrated into websites, social media platforms, messaging apps, virtual assistants, like Facebook Messenger or WhatsApp. The use cases of public chatbots, customer service, like providing support to customers by answering FAQs, processing orders, handling complaints, marketing. Engaging potential customers through promotions, quizzes, interactive content. Informational dissemination means offering real-time information on news, weather, stock prices, and entertainment. LMs are used in entertainment, like engaging users with games, storytelling, interactive fiction, and so on. I've already mentioned Siri, Alexa, and Google Assistants. These are voice-activated public chatbots available to wide audiences, and chatbots on social media, like the ones deployed, by Facebook Messenger. They are also helping customers. The data privacy. So public chatbots often operate under strict data privacy regulations and policies to protect the user data. They generally collect data to improve user experience, but must comply with laws like GDPR in Europe. And I also like to emphasize that one has to be really cautious when uploading documents, pictures to ChatGPT, for example. But the prompts, definitely shouldn't contain any confidential info either. Large language models are collecting documents from many sources and are trained on a variety of textual data from numerous sources. So these sources typically include publicly available text, or for example from web scraping. So these LLMs are often trained on vast data sets that include publicly available content, from websites, blogs, online publications. Also from books, like these digitized books from diverse genres, including fiction, non-fiction, textbooks, encyclopedias, academic papers. So these LLMs are often trained also on research papers from sources like Arxiv and other academic repositories like PubMed. And Wikipedia, it's a major resource due to its breadth of information across many languages and topics. Common Crawl is the second one. So it's a large-scale web crawler that periodically captures the snapshots of the internet. The resulting dataset contains millions of web pages, even billions, which can serve as a training resource for large language models. Social media posts, from X, Facebook, Reddit, other discussion boards are sometimes part of the data collection process. News articles, so articles from news sources, magazines, journalism platforms help understand current events. Code repositories, so for code-related models, these repositories from GitLab, GitHub, Bitbucket provide access to open source code, enabling the models to learn coding patterns, syntaxes, best practices. Government and legal documents, so like government publications, legislative documents, court rulings, legal text, these kinds of things. User-generated content, reviews, comments, forum posts, that are publicly accessible. Multilingual corpora, so large data sets are built from sources in multiple language to create multilingual models that understand and translates across languages. Specialized databases, these can include medical databases, finance reports, patents, and industry-specific documents, and finally the curated data sets. So many LLMs use carefully selected and curated data sets designed to improve language understanding in specific contexts, domains or languages. So our LLM solution has built-in RAG option as well. So let's see what it is. This RAG is a retrieval augmented generation. It's a technique in LLMs that combines both the retrieval-based and generative approaches to improve the performance. So, these are particularly in tasks requiring factual accuracy and domain-specific knowledge. So what do these mean? You can see that one of the key components is a retrieval component. So the model first retrieves the relevant information from an external source, such as database, search index, collection of documents that I mentioned in the previous slides, and this step enhances the model's ability to access specific up-to-date and detailed knowledge that may not be contained in the training data. And this generative component, after it retrieved the relevant documents or pieces of information, then the model generates a response based on both the retrieved data and the learned language patterns. So the generation is guided or informed by the information fetched during the retrieval step. How it works, so the first one is the query input. The user provides a query or prompt. Second one is document retrieval, where the model retrieves the most relevant documents or facts from an external database. And the third one is the response generation, where the using both the retrieve information and its own language capabilities, the model generates a coherent and accurate response. So the advantage is this factual accuracy, as I mentioned. The retrieval process here ensures that the model has access to up-to-date domain-specific knowledge. Scalability means that this RAG allows models to handle much larger body of knowledge than what can be encoded in the model itself. And the dynamic knowledge update, since the retrieval process fetches information from external sources, it enables models to handle recent events or facts that may not be part of the original data set. So in short, this RAG is a way of augmenting large language models with external information, to enhance the accuracy of the model. So we use the state-of-the-art Ollama platform to build our LLM solutions. So you can have the question what this Ollama is. It's a platform that provides tools and infrastructure for deploying LLMs locally on the user's machine. So it aims to make easier for developers to use and run sophisticated AI models without relying on cloud infrastructure. So these local LLMs, Ollama allows users to run large language models directly on their local machines, including powerful LLMs on various tasks, like text generation, question answering, summarization, privacy and control. Running the model locally, something popped up that I was removed, so sorry about that. So back to privacy and control. Running models locally means users have greater control over their data, as they do not need to send any information to the cloud. Pre-built models, Ollama provides pre-built and pre-trained models that can be fine-tuned or customized for specific use cases, efficiency. So Ollama optimizes the models for performance, so the user doesn't really need, specialized hardware like GPUs. And the flexibility, so the platform also supports various models that can be used for different AI tasks like language understanding, code generation, content creation. So use cases, developers can use Ollama to integrate AI-powered features on-premise, directly into their applications. Companies can benefit from the privacy of running models on premises, avoiding the data sharing with third-party cloud providers, and individuals who want to explore or use AI without needing cloud subscriptions can access advanced AI locally. So we also developed a chatbot. So these LLMs are transforming various sectors and improving the way we interact with technology and information. It's important because most of our competitors have it. So we need to also present a solution. So last week I was in the World Summit AI where we presented this chatbot. It was a very big hype this year and last year as well. So now it's time to utilize and implement production solutions. So Open Telekom Cloud also produced one, or OTC LLM demo provides a use case like that. So we integrated a single language model with translators, like, we didn't need a multi-language model, just a simple translator flow, and also developed a text-to-speech and speech-to-text interface. And with this application, we can also demonstrate to our customers how the different cloud technologies and DevOps technologies can work together with AI in a real life example. So let's see the demo part. Here you can see our chatbot LLM solution. So Magenta Smart Chat is its name, and I would emphasize its rock button, as you can see there. So basically, this is where we can upload documents, text documents, and in the backend, the text gets extracted, and right after the upload, we can ask questions from the uploaded documents. So before the recording, I uploaded documentation from our AI service ModelArts, also from MapQuery service, and a simple article about the Kubernetes templating engine Helm. You can see there the basic question and answer. So first, I will ask what ModelArts is, or AI service ModelArts. You can see that almost immediately the answer is there. So it was in English. We can see that the RAG component is working. Now let's see one question regarding MRS, MapReduce service. So carbon data, as many of you know, it's a component of MapReduce service. So I asked a question in German. How can I use the carbon data? As you can see, also in a couple of seconds, the answer is there that MRS is supporting the self-developed carbon data technology. The last question is in Spanish. So let's see the Spanish translation works as well or not. How can I install Helm? As you can see, this is the question in Spanish, and in a couple of seconds, since I uploaded the Helm article, it also should produce the different steps in great details, how we can install the Kubernetes templating engine Helm. So that's about it, my part, and with this, I'm handing over the stage to you, Zsolt.
Thank you very much, Feri.
We're collecting the questions and put in a joint Q&A session after Zsolt's talk, just to let you know.
Thank you very much, Niels. So my presentation would focus to the deployment of our chatbot application and the underlying technologies. The agenda during my speech, I will start with an OpenStack overview and some words about our OTC OpenStack implementation. Then I will introduce the Terraform and explain how we are using for the infrastructure of deployment of the OTC LLM chat application. Finally, I will demonstrate the application deployment using Helm charts, including the Libre Translate, Ollama, and the Chatbot application. The infrastructure, the application deployment would end with a short demo. So the technology stack, what I would cover during my presentation, the infrastructure host is an OpenStack. The infrastructure deployment, we are using Terraform. The application data store is the package manager is Helm. The CI/CD tool is GitHub CI. The RAG tool is a vector store index and the OTC OpenSearch. The library is Ollama, simple directory there, and the vector store index. And the LLM model is a Llama tree. And the web GUI is, as you see in Feri's page, is HTML and vanilla JavaScript. So we are using OpenStack. So what is OpenStack? OpenStack is a leading open source cloud computing platform to support virtual machines, containers, and bare metal workloads. It can be deployed in on-premises, public clouds, or in edge locations. OpenStack is massively horizontally scalable and suitable for larger deployments, and additionally, OpenStack supports high availability and fault tolerance, ensuring their reliable operations. Some words about our OTC OpenStack implementation. In OTC, we're utilizing the cascaded architecture. This means is a hierarchical architecture which implemented to enhance the scalability and the reliability. In OTC, we have 2 regions and 3 availability zones. So the core component is redundant per availability zone. Additionally, we introduced the cell architecture, which would be duplicates the core components within each cell. So with this implementation, we could achieve more fault tolerant and we could improve the high availability. Let's jump to the infrastructure deployment part. So we are using Terraform. And what is Terraform? Terraform is an industry leader infrastructure as a code and automation on cloud to support multiple cloud providers like Amazon, Azure, Google Cloud, or Oracle, and of course it's OTC. Provide easy to understand HashiCorp configuration language and provide state management for the deployment and easy integration with the automation pipeline. Common way to interact with the Terraform to using command line interface. We can use several subcommands like Terraform init to initializing the deployment and downloading the dependency modules. Terraform validate our source code. Terraform plan is generating the plan file. This would be describe the planned architecture, and the Terraform apply the command which would deploy the infrastructure itself. And the Terraform output, we could get the result of our deployment. And the Terraform destroyed our infrastructure. The providers, to very important part of the infra deployment to specify the provider implement the functionality to interact with the cloud service like network services, compute services like Kubernetes clusters, or even databases or caches or whatever components. In the backend, our deployment is responsible for store the state of the infrastructure deployment. We supporting the following backends is a local file, object storage, GitHub registry or databases. Anyway, the GitHub registry is also using HTTP types. And in production environment, anyway, we recommend to use S3 or database backend. Very important part of the cloud native deployment, the well-defined network architecture. We could simply deploy the network components via Terraform to including a network, subnetwork, Elastic IP, VPC peering, load balancers, whatever. And these resources would just used by the compute components later. I will show in the next slides. So even the most important part of the infrastructure deployment, the multi-node Kubernetes cluster in OTC anyway, we call it a cloud container engine. To deploy the Kubernetes, we have to specify some information like network components I presented before, so VPC ID, subnet ID. But we also have to specify the node flavor in CPU node. That would be a simple flavor. In GPU node, we have to specify a dedicated flavor for that. And in GPU node, we have to also specify the GPU driver. This is very similar in other cloud providers, so that could be very useful information for you. In professional environment, it's more efficient to allocate the workload based on the specific purpose of the application. So it means the simple web servers and application servers should be deployed to the CPU node, and the AI application, so the LLM application or the AI translators should deploy to the GPU node to here. So in that way, we could utilize the GPU capabilities, and of course, so we are not losing money with that. So the Terraform outputs provide the result of the deployment and provides information about the deployed infrastructure in case the output of the Kubernetes is the simple kube config. But this could be an Elastic IP or DNS address or whatever what we want. Let's jump to our short demo. So first we have to define the cloud credential. could log into the code. Then with the Terraform init command, we are downloading the dependencies. Then the Terraform validate command, we are validating our source code. It looks like everything okay. Then the Terraform plan, we are generating the plan file, which would be the describe the plan architecture. Then the Terraform apply command, which would deploy the infrastructure itself. This would take between 1-2 minutes to half an hour. It depends on the size of your infrastructure. And when the infrastructure is deployed, we could verify the Kubernetes cluster, so it's up and running. And even in the GPU node, we could verify the GPU driver is installed and everything okay with that. And as we see, it looks like everything fine now. Okay, so let's jump to the Helm deployment. In the next chapter, in the application deployment is using Helm. In production environment, we would integrate this to the CI/CD pipeline, but for better understanding and its demonstration purposes, I will just present with a simple Helm command line deployment. So is Helm. So what is Helm? The Helm is the best way to find shared software for Kubernetes. Its key features the templating, store common definition in separate file, use package management, provide version control, and it has a very big support community around it. So we could find mostly every application wrapper for Helm. So in critical point of the LM application, the scalability of the system. If we have to serve bigger workloads, then we have to build bigger infrastructure. This means we have to deploy additional instances of our Chatbot, Ulama, and the Libre Translate application. But for the operation of these pods require downloading LLM models and multi-language files, which can cause startup delay or huge data transfer. So these files are quite huge. If we have to download a lot of files, then that is a lot of data transfer. To mitigate this issue, we should use a common storage with the persistent volumes with a S3 compatible backend. You could use other solution, but this is the simplest one and let's say the cheapest one. So in here, you have to specify the FS type is STFS, and you have to specify the bucket name in here. This allows to the pods download the model files and transaction files only once, and the next instances, when the instance is starting, then just reuse them. So they already download model files or translation files. So in that way, we could reach much faster boot times and reduce data transfer. And of course, your infrastructure, it costs less money. So we are also using config maps to store non-confidential data as a key value pairs. Pods can get config maps as environment variables, command line arguments, or even configuration file placed in somewhere in the volume. Secret is a small object, contains small amount of sensitive data like password, tokens, secret keys. Yeah, this is stored in base64 encoded format, but in our environment, usually we are encoding, we are using via Vault, but this is not part of the presentation. But in professional environment, it's better to integrate with other tool. Let's jump to the Libre Translate deployment. So what is Libre Translate? It's an open source machine transaction engine based on Argo Translate, and anyway written in Django, and using stateful set for the deployment as you see, and using init container to download the language files. As you see here, the init container, it supports GPU containers and even support more than 100 language combination. In our demo, we are just using English, Spanish, Hungarian, and German language combinations. And here in the Django code is install models, only downloading the necessary language combinations to the persistent volume. Let's jump to the RAG. So what is RAG? Ferry already explained the theory of the RAG. For this demo, we are using a simple Llama indexer to provide the vector database functionality. For larger infrastructure, we recommend to using managed services like OpenSearch. Anyway, in OTC, we are also offer managed OpenSearch, but could utilize to build the professional and scalable RAG solutions. So the Olama deployment. So it's using a deployment type, also using init container, as you see, to download the model files to the persistent volume. The models which we are using for that is a Llama 3 and the embedded model for that. And it's also important to mention here what kind of information you have to define to utilizing the GPU containers. So this LD library part, NVIDIA driver capabilities, and NVIDIA visible devices should be defined to you could utilize the GPU capabilities. Already explained also the Olama functionality shortly, but if you are using the Helm Olama, most probably you don't want to interact with the Olama containers. But in case you want to do some experimenting or do some manual testing, you could do this to directly with logging into the Olama containers. So you could do even list the available models, start serving any of the models, download additional models, or even just call the model inference with a curl command, with this curl API-chat endpoint, or even inference your model via command line. So very useful tool for that. And finally, jump to the LLM chat application deployment. The deployment using init containers to wait the Olama and the River translator up and running, and also responsible to indexing the RAG vector database. And as you see here, it's a defined volume in the persistent volume, the RAG path, and the web application just upload the files there, and then the application do the indexing if necessary. And in here, we have to wait to the Olama and the Libre Translate pods are running. Then also the indexing of the RAG files is finished. Then the application is up and running. Let's jump to the demo here. Deployment of the application. So first we are checking the application is deployed or not. Of course, we not deployed the application, so not find any application. Then we are deploy the persistent volume manually advanced. So that way we could do much safer operation. And then when the persistent volume ready, then we could deploy the application itself with a Helm upgrade command. Then this could take several minutes. It depends to how much time need to download the LLM models or the translation files, or even how much file in your RAG directory. And when our action is done, the application is up and running, as you see here. Let's jump to the application. So I already presented a short demo of our application. We could ask any question related to the RAG files, but even we could get some general question, for example, related to the Star Wars Chewbacca, as you see here. So we could use the RAG functionality, but we could use the base model knowledge also. And that way, how we could build a simpler application in own RAG files. Thank you very much. That's all for me.
Thanks, Zsolt, and thanks also, Ferenc. We have a couple of questions here, and I just want to remind you that you can ask a question also directly. If you want to do that, just click on one of those hand symbol, and then we will turn on your microphone so that you can talk directly. But in the meantime, we can just have a look. We have a couple of questions already in the chat. So for example, there was a question, what are the advantages of using Libre Translate in the pipeline? Wouldn't it be better to use a multi-language, a multilingual model in this case?
Let me try to answer that one. So I think nowadays, because a lot of models are in English, so not many multilingual models. Training a multi-language model takes up a lot of resource. So they are really huge. They can be really big size in the end. We don't really had that much space nor the resource. So our LLM solution is rather a small footprint up. It can run on a small machine. Like, as I know, Llama 3 knows 11 languages, but with this open source Libre Translate solution that we use, we can answer questions on many more languages.
Mm-hmm. And what size are we talking here about in current models?
Yes. So as I know, the multilingual models can be tens or even hundreds of gigabytes. Because with using billions of parameters tuned, but since we are using Libre Translate for our single language model, our model is only 400, 500 megabytes.
Good. Let me see what else is here. Why should we use LLM chat instead of ChatGPT? Someone asks.
I think GDPR is one of the key points, and data stays not only in Europe, but it doesn't go overseas, of course, but also the data also stays on your private machine, even on premises. So that is, I think, a very, very good and big advantage.
Yes, indeed, and I think that question was also already be discussed in the public chat as well. But so we have also an official answer on that. There's a question probably to Zsolt, but we have a private environment and cannot download large and translation models from the public internet. How can we deploy this solution under these circumstances?
Yeah, it's a very good question. So that was the reason why we are using persistent volumes. So we could upload our models advanced to the persistent volumes. So the Ulama and the Libre Translate container just pick up from there. So don't need the internet connection to the operation. So it's in that way you could use in on-premises or even in public code when you don't have an internet connection.
So somebody appears to be very appealed by your solution and asked, can this solution also be deployed either on premises or on other hyperscaler cloud platforms like Azure or AWS or something like that?
Yes, I think this is again belongs to me. Yes, it can be deployed, but the Terraform modules and also the Helm charts need to modify a little bit. So not one-to-one could use in other hyperscalers. It needs some modification, but just a little work. I think it's not so big work, and then also could deploy to other hyperscalers or on premises.
So that means it works, but why not just leave it just in Europe and use either some local or a sovereign solution like the OTC if that marketing remark is okay. I think we have, are there some other questions? Yeah, maybe an interesting question. How can we integrate this solution into a CI/CD pipeline?
We already did this integration. So first, it's using the Terraform Helm driver. So we integrate the Terraform with the Helm. So that's already we did that, and then additionally was also integrated to the GitHub CI. So when any change in the code of the application or even in the Helm package, then the GitHub CI would redeploy automatically and do the reindexing if it's necessary.
So if I see that correctly, we have covered all questions so far. Thanks a lot to you guys. And I'd like to head back to you, Zoltan, so for some final words.
Yeah, sure. So thanks for everyone for joining today's meetup and the many very good questions that we received. And of course, special thanks to Vincent, Arik, Ferenc and Zsolt for the insightful presentations and demos. Don't forget to join the community on meetup.com so you will get notifications about any future events. We plan having an in-person meetup in Munich probably in December or early next year, and a similar online event in February next year. And remember, the recording of this meetup will be available on the Clouders Club YouTube channel in a few days' time. So as mentioned, you can find the link to the channel. And with that words, thank you for joining and see you next time. Bye.